Welcome to this video on the functions and subjective testing of flight simulation training devices. You will learn the basic philosophy of this testing. For more details, such as the required tests, please refer to the requirements applicable to your organization and device. We use two different testing methods to ensure that the flight simulation training device works correctly, supports positive training, and complies with the requirements. The first method is called objective testing. As the name suggests, objective testing aims for quantifiable outcomes with minimal room for personal opinions or interpretations. For flight simulators, the approach is straightforward. We compare the training device to the real aircraft. For example, we have recorded data from an actual airplane takeoff showing the acceleration of airspeed and the increase in pitch angle for rotation. We then compare the simulator's takeoff behavior to this data, including parameters such as flight control inputs, engine thrust, heading, altitude, and so on. This comparison is achieved by overlaying the simulator's results with the flight test data. Like this. Now it is easy and objective to compare if there is a difference between the simulator and real aircraft. The requirements also specify tolerances. If a test result falls outside these tolerances, it is deemed as a failure and corrective actions are necessary. The process is essentially binary. Either the test passes or it fails. This is a hallmark of objective testing. To avoid the time-consuming process of having a pilot performing these tests with high precision, they are typically conducted automatically. Software provides certain flight control inputs or flies certain maneuvers and records the results, ensuring an effective comparison of the simulator to the aircraft. Now, let's move on to the second test method, known as functions and subjective testing. This testing is performed by humans. They fly the device, assess how it feels and behaves, and evaluate the functionality of the avionics systems. As the name suggests, this method has two aspects, functional testing and subjective testing. Let's first discuss the subjective testing. Subjective testing is performed by a pilot with the appropriate license to fly the simulated aircraft. The pilot should also be knowledgeable about the FSTD technical requirements to understand what is expected from the device in question. In short, subjective testing involves flying the training device and using all your senses to evaluate if the device feels appropriate and supports positive training. Here are a few important questions the pilot should keep in mind during the testing. Does the device fly like a real aircraft? Is it as easy or difficult to fly as the actual aircraft? Are the visual, auditory, motion, and tactile cues realistic? How does this device differ from the real aircraft? Where are the differences most noticeable? Does the device support positive training? Now you will see a demonstration of how to conduct subjective testing. An expert pilot is performing subjective testing on some manual handling.
Aircraft is flying about 13,000 feet. We are going to do steep turns, exercise. Autopilot is now disconnected. I take my hands off. As you see, we need a little bit nose down trim to keep 13,000 feet, to keep it steady. There we go. Release my hands, it's in trim. I'm going to start banking to the right. $20 degrees, 30 degrees, a little bit of pull needed, increasing to 45 degrees, more pull needed. If I increase more, we should have a warning.
Bank angle.
Bank angle warning. Back to 45 degrees. Everything feels normal. Approaching heading. A little bit push needed. Stay 13,000. Now I'm reducing power. Gear warning. As the speed decreases, more trim needed. I'm reducing to 130 knots. More trim needed. 130 knots, almost in the trim. Going back to 13,000. Less power needed for yoke, for the bank, as it should be. As in trim, increasing power. Hands off. As the speed increases, aircraft keeps climbing, and trim needed. Back to the original heading. Everything feels as it should be.
What did you think of the video? The pilot clearly communicated his actions, observations, and whether the device's behavior matched his expectations. He addressed one aspect at a time. He noted basic phenomena such as changes in control forces, trim settings, pitch tendencies, and so on. Subjective testing is a collaborative effort, and his communication supported the other team members in understanding the situation. As you recall, this testing method is called functions and subjective testing. The term functions refers to evaluating how the systems operate. This leads us to the discussion how we should check the systems and avionics as part of the functions and subjective testing. Let's look at an example of functions testing. We will use this computer simulation of an Airbus A320. In this example, we are testing for a hydraulic leak. We start by checking the cockpit for any active cautions or warnings. We then review the overhead panel, noting that there are no lights on the push buttons, indicating that the systems are functioning normally. In this aircraft type, system synoptics and status information are displayed on the lower display. Let's focus on this display. The upper display shows the primary engine parameters. Currently, the lower display provides additional engine parameters such as fuel usage, engine oil capacity, oil pressure, temperature, and engine vibrations. We can select different system synoptics to display on the lower screen. Let's take a closer look at this display. This is a better viewing angle. Let's use a push button to view the information on the hydraulic system on this display. As you can see, this aircraft has 3 hydraulic systems identified. The hydraulic lines are shown in green, indicating that the systems are operating normally. The systems are labeled as green, blue, and yellow. Below their names, we see that the pressure in each system is 3,000 pounds per square inch (psi). PTU stands for Power Transfer Unit. If the green or yellow system loses pressure, the PTU can pressurize the other system. This symbol indicates that the PTU is not currently transferring pressure. The rectangles represent engine-driven hydraulic pumps, and the circles below them are valves that can be closed, for example, in case of an engine fire. At the bottom, a green pointer shows the hydraulic fluid quantity in the reservoir. We will soon introduce a malfunction to simulate a hydraulic leak in the green system. Before doing so, we need to review what is to expect when the malfunction is activated. Testing is meaningful only if we have clear expectations and can compare the device's performance to written specifications. So, let's consult the pilot manuals to understand the expected behavior of the system in case of a hydraulic leak or failure. We open the manual and start studying it. Let's look a little closer. By reviewing the manual for the hydraulic system, it is easy to identify things that we should see happening in our device. Some examples are highlighted here. It is crucial to refer to these pieces of information when testing our training device. If the device does not operate as described in the pilot manuals, students may not learn correctly. In fact, they might develop an incorrect understanding of the aircraft systems, which could lead to hazards, incidents, or accidents when operating real aircraft. This is known as negative training. Our goal is to ensure that the training device functions correctly to prevent negative training. An important part of this process is to objectively compare the device's performance with the pilot manuals. If the device does not perform correctly, corrective actions must be taken. By reviewing the manual, we can summarize everything we should see, hear, and experience when a hydraulic leak happens. We find the following facts. An amber fault light on the overhead panel should be lit on the engine-driven pump push button when the fluid level in the reservoir is low. The hydraulic schematics should show low to indicate a low pressure. The hydraulic schematics label should change its color to amber. The power transfer unit should activate automatically, but it is unable to pressurize the green system since it will have lost its fluid, so there should be a caution on this. A textual caution message should appear. A master caution light should be lit. A single chime oral warning should be heard. And we noted that the hydraulic system failure certainly affects other systems. We should experience that the normal extension of the landing gear should not be possible. And some flight control servo actuators that use the green hydraulic system are not operating. Now we have briefed ourselves on what to expect. Let's get back into the cockpit. Now let's observe the effects of a hydraulic leak in the green system. Watch the pointer indicating the fluid level. The leak has been activated. We see that the fluid level is dropping, simulating a leak. This appears to be functioning as expected. As the fluid level decreases enough, hydraulic pressure should also be lost. Let's continue monitoring. Notice how the pointer changes its color to amber. The pressure is now dropping rapidly due to the lack of fluid. The PTU activates to try to maintain pressure in the green system. The system's color changes to amber except for the hydraulic pump, which remains green. It was expected that the entire pump symbol would change to amber, so this indication seems incorrect. Let's check the overhead panel for further indications. This is the overhead panel. There is an amber fault light on the green system pump push button, just as was told in the manual, so that is okay. There is another amber fault light. It indicates that the PTU could not pressurize the green system because it didn't have any fluid. This is okay also. Let's lean back a little and see the whole cockpit. Wait a second, we should have a master caution light lit here, but that is missing. And we should have a textual caution message here, but that is missing too. This does not look good. We have identified issues that have to be corrected in this device. Let's see how the hydraulic system is integrated into the other systems. We can select the flight control page to this display. Here we see symbols representing various flight control surfaces, such as spoilers, ailerons, elevators, pitch trim, and rudder. These surfaces are powered by hydraulic systems. Each surface typically has at least two actuators powered by different hydraulic systems. Many actuators are marked with amber, indicating that they are not operational. This seems to be correct. We should also evaluate how the aircraft handles with this malfunction. Pilots may not notice any difference in handling due to one hydraulic system failure, but we need to verify this. Additionally, there is an important system test remaining. According to the manual, the landing gear is operated by the green hydraulic system. With this system inoperative, we expect that the landing gear should not move when the gear lever is selected to the down position. Let's move the gear lever and observe the landing gear lights. The landing gear lights turn amber. Wait a minute. When the gear lever was lowered, the hydraulic system regained pressure. This is incorrect. The fluid is lost, so there should be no pressure. Additionally, the lights indicate that the landing gear is down and locked. This is unrealistic. If this was a real training device, we would have several issues that need to be corrected before it could be used for hydraulic system training. Hopefully this demonstration has helped you in understanding the concept of functions testing. You might wonder why we discussed objective testing when it is not the main focus of this video. Objective testing is an effective method but only evaluates the device under specific conditions. In contrast, functions and subjective testing can be conducted under a wide range of conditions. Let's illustrate this. For instance, weight is a crucial factor for any aircraft. Objective testing typically involves a limited number of takeoff tests at a few different weights. However, functions and subjective testing can be performed at any weight, allowing for a much greater range of conditions. The same applies to the center of gravity. Objective takeoff tests use a few different center of gravity positions, whereas subjective testing can accommodate any position. the number of possible center of gravity conditions is much larger. Again, same applies for airspeed and altitude and for the winds and for the flight control system conditions. For example, the flap setting, stability augmentation level, fly-by-wire system status, yaw damper state, flight envelope protection functions and their reversionary modes and failures strongly affects the handling characteristics of an aircraft. We could draw even more parameters to the image, but you get the idea already. Objective testing is an accurate and effective way of testing a training device, but it tests the device only in a few different conditions. In other words, it only samples a small portion of the whole flight envelope. Functions and subjective testing can be used to evaluate the aircraft under any conditions throughout the entire flight envelope. It is important that you document the conditions and configurations used in your tests so that you can refer to them later and systematically check different parts of the envelope during the next functions and subjective test flights. While subjective testing is based on personal opinion and is thus less precise than objective testing, it complements objective testing effectively. Objective tests ensure that the training device performs correctly under specified conditions. Subjective testing then verifies if the simulation feels realistic across a broader range of conditions. Conversely, if there are subjective concerns, objective testing can provide further insight. For example, if you find that the training device feels too sensitive to the pilot inputs, objective testing can help evaluate this issue more thoroughly. As you see, objective testing and functions and subjective testing support each other. We should not think of them as fully separate processes. Whenever possible, we should test the device using these two test methods together. When these two processes overlap, when we use the two processes together, our work is pure gold. It leads us to the best possible results. You too can find this gold. By following these best testing practices, we can ensure that our training device supports positive training under all conditions.